In this video we are going to see synchronization hardware. The previous two videos we have seen what are process synchronization, why we need process synchronization, and what are the different synchronization mechanism, and we have seen what is Peterson solution, how Peterson solution is satisfying with the mutual exclusion, progress and bounded waiting. Here we are going to see different synchronization hardware. And the subject code is same 18CS43 and the syllabus is process synchronization, Peterson solution, synchronization hardware, Semaphore, classical problems of synchronization, monitors, and the synchronization Peterson solution already we finished. In this video we are going to see synchronization hardware and Semaphores and classical problems of synchronization, monitors will see in the coming videos. Prerequisite is knowledge about process scheduling. And the objective of this video is test and set instructions, Semaphore. These two are the hardware instructions. Synchronization hardware, test and set instruction. Test and set instruction is a kernel side instruction, and here the first left hand side algorithm is the definition for test and set instruction. Right hand side algorithm is the how test and set instruction can be used to preserve mutual exclusion. Test and set instruction, actually test and set instruction is working atomically. The target variable, value of the target variable is copied to another variable RV, then we have to keep target variable as true. That is the definition for test and set. When you are executing test and set, these two things are happening. Take the value from target variable, copy to RV, then keep target variable as true. These two things are happening when you are executing test and set, and it is kernel side, we cannot preempt. That indicate when one particular process execute test and set, another process cannot preempt test and set. That is the left hand side algorithm, and right hand side algorithm is the implementation of test and set instruction to how to preserve mutual exclusion with the help of test and set. Here test and set variable is lock, initial value of lock is false. So when you are executing test and set lock variable copied to one register, then again lock variable is initialized with the value true. Then at a time only one process can execute that, right? Another process cannot preempt it. So at a time only one process will be there inside critical section, no other process. So it is preserving mutual exclusion. And here how test and set instruction is going to preserve progress and bounded waiting. See, there are and this set, the difference between test and set and Peterson is test and set can be applied for multiple instructions, multiple process. Peterson can be applied only for two process. So waiting is a array size is number of process. Waiting of I is equal to true and k is equal to true, and if one process wanted to process test and set, first it has to pass one condition. That condition is waiting of I and key. If they process that particular while loop condition, it can process test and set ampersand lock. Once it process test and set ampersand lock, they are making waiting of I is equal to false, then it can go to critical section. After coming from critical section, then see how to preserve progress and bounded waiting. Suppose there are four processes, for size it is implemented as a circular queue. So 1, 2, 3, 4. After 4 again first process will be getting chance. For that we are making j is equal to I plus 1 percentage n, while j is not equal to I and j and waiting of j not equal to true, then only j will be j plus 1 percentage n. So all process will get the chance 1, 2, 3, 4. After that again 1, 2, 3, 4 all will get the chance. In that way we can preserved progress and bounded waiting using test and set instructions. Next one is Semaphore. Semaphore is a simple integer variable. It is used to provide synchronization among multiple processes running concurrently. There are two types of semaphores, counting semaphore and binary semaphore. Binary semaphore is also known as mutex, and counting semaphore variable can take any value. Binary semaphore can be take only 0 and 1. And there are two atomic operations, wait operation and signal operation. And wait operation, how wait operation is implemented is while s less than or equal to 0, then no operation, Otherwise, if your S is greater than 0, then S is decremented. In this way, you are going to implement wait operation. What is S? S is a semaphore variable, and in practically what is semaphore variable is, suppose I have one resource name is R1, and I have 10 copies of resource R1, then S will be 10. Initial value of S will be 10. That indicates that particular resource I have 10 copies. Then suppose one process has come. That process need that particular resource R1. Then we have to see whether R1 is available or not. Currently I have 10 copies of R1. So S value is greater than 0, right? I have 10 copies. R1 is 10 copies. So S is indicating how many copies of R1. So here R1 is 10. That indicates S value is greater than 0. So I can give one copy of R1 to my process. I am giving one copy of R1 to my process. So 10 is decrement to 9. That way here S also decremented. So now S is 9. Understood? Then suppose another process came. That process need R2. R2, I don't have any copy of R2. R2 is 0 here. So I am not able to give resource for that particular process, right? So my S value is less than or equal to 0 here. No resource, that particular resource is not available. So that process has to wait until and unless they get the resources. That is the meaning of S less than or equal to 0, no operation. S means how many resources how many copies of the resource are available. If no copies are available, we are not able to give that resource to process. So that process has to wait. If I may, S greater than 0 means that particular resource is available. So give one copy of the resource to that particular process and decrement the number of resources. Then signal of S. Signal of S is S++. That we will see how it is working is in the coming slides we can see. These are the two atomic operations, wait and signal inside semaphore. Mutual exclusion implementation with the semaphore. See, in the previous video I told you to enter the critical section, process wanted to pass entry section. After critical section they have to go through the exit section. Here entry section is waiting and the exit section is signal. Waiting is, we know they are asking for the resources. If you have resources, give it. Otherwise the process has to wait. That is waiting. Suppose there are two processes came, P1 and P2. P1 need one resources R1, P2 also need one resources R1, and P1 came first. I had only one copy of R1, I gave. So waiting, P1 can pass the entry section. It is inside the critical section. But for P2 that particular resource is not available. So S is less than 0. S is less than 0 means it has to wait. It cannot go to critical section. Then signal. Signal mutex means after coming from critical section. After coming from critical section, that particular process, they have to leave their resources. They are leaving their resources. So the resource number is incrementing. So in the previous slide I told you signal means we are incrementing S. S++ means, right. So that process had one resource. They used that resources. Now they came from the critical section. Now it is the time to leave the resources. When they are leaving the resources, they can increment. I hope all of you understood. Define semaphore as tree struct typed as struct int values struct process list semaphore. Int value is, this is the way we are going to define semaphore as C struct, and there are two variables, value variable and one linked list. And value is how many resources are available, and list is that is the waiting list, which all process in the waiting list. Suppose the one process came, there is no resources, mean he has to wait in the waiting list. So that waiting list can hold the process which is coming for the waiting. See here wait and signal we are going to explain in detail. Wait semaphore is S value, like first we are decrementing. We have 1, so we have given that resources to process. So I am decrementing the value of 1 value. After decrementing, how to see whether it is less than 0 or not. If it is less than 0, my process has to wait in the list. Then I am blocking that process. If it is not less than 0, that process can execute their operation. in signal, after critical section process is going to execute the signal operation, right? So after critical section means they completed their work, so they can leave their variable. So when they are leaving their variable, total number of variable count is incrementing, so S value is incrementing.